So we are going to start chapter 6, then you have to make sure that we have been through the word sup, for instance, sup, in. Then least upper bound, greatest lower bound. They are real analysis words. Very important. Cauchy sequence. Because according to what happens is that according to this book, there is we don't have an opportunity to put the emphasis on the analysis taste. So that is a big disadvantage. Actually, it seems that I am not a lecturer here, actually. If somebody from Columbia University listen to me, they may wonder, oh, maybe Dr. Ramasinghe got older, so now he cannot teach. Yeah, it is that different actually to me. So before we start chapter 6, let's spend some minutes, say, or even half an hour, about the important words. Now, if you have not the empty set, if you get a non-empty subset of R which is bounded above, you know the meaning of sup. Can you say it is in English? Say he is a subset of R which is bounded above. So what is in your head about the sup? I don't ask him because he was in a trip, no. He will say, sir, I know about chicken soup. What is in your head about the soup? Could you say? What is in your head about soup? You know, I'm asking the impression you have.
It is the largest bowl, which is close to the upper bound.
The upper bound is not unique, so your answer is not does not convey anything.
The least upper.
Yeah, of course. I mean, sup is the short form of least upper bound. So, what is in your head about the least upper bound? What comes to your head? For instance, let's say, suppose I get E is equal to 0, 1. So what is the sup of this set? What is sup? Sup A is what? What is it? You did not study this?
No, I was doing the other homework from the previous chapter. Again.
You haven't studied it. Then we cannot have this discussion. You have been doing homework on what chapter?
Fourth one actually.
Chapter 4. Chapter 4, let's see whether if you haven't studied, it doesn't make any sense to discuss about chapter 4. You don't go to anything like soup and this and that. You don't go. So you are really behind in a sense. You don't, I mean, both of you cannot say what the soup is. Soup is. What about you?
I can say exact number because it's close to not one. It is the closest
You said, however, soup A is the least upper bound. Can you give me an upper bound of this word?
1 is the lowest upper.
So the soup must be 1 over there. Am I going too fast?
No, actually the thing is the gap between the lesson and the homework, so
Makes
yeah.
Because some homework problems, though they are not difficult, they are difficult to write answers. I mean, many questions are not deep questions because, however, to write the answer, you need to really spend time. Oh, okay. I don't know, I have a problem then how I cannot, because Prabhat wants me to, cover as many. Because this is not the style that I lecture, usually. Because when I lecture, students learn about what I lecture the same day at the spot, because I spend time and I give examples. We have to follow the book. This book is not analysis based. It is really, basics. He wants to improve the basics. So much so that I behave in a completely different way. Yeah, so I was actually wondering then, for instance, as you said, one is an upper bound, one is the smallest upper bound. Can you remember the meaning of? No, you cannot remember, no? Do you?
So every upper bound needs to be bigger than the least upper bound. So that least upper bound is the supreme.
Yeah, least upper bound is an upper bound to start with, and if you take any other upper bound, it must be greater than or equal to the least upper bound. No, that's the definition. You are looking different actually.
I changed my glasses as well.
Yeah, I cannot recognize you. Yeah, finding it difficult. Book is difficult, you are difficult. I don't know, because I want to satisfy him. Otherwise, I like to spend so much of time on these theorems. Anyway, let's try to see, since I started it, because you gave me the definition of, you know the meaning of an upper bound. Upper bound is, if you say lambda is an upper bound of E, every element of E must be less than or equal to lambda. That is the meaning of an upper bound. Then you said the least upper bound is an upper bound, but if you take any other upper bound, it must be greater than or equal to least upper bound. So from that onwards, you said least upper bound is 1, but you couldn't say sup is 1 because you have forgotten even sup and least upper bound mean the same thing. Another thing, by the way, in Colombo University, because most of the students, except 1 or 2, at the most 2 maybe, yes, Sinhala students, so I go kind of bilingual my lecture, because sometimes I remember very well, I was explaining something in English lecture. It's a general degree lecture, not the special. They could not understand. After 10-15 minutes, I said, in Sinhala. Then one daughter was said, oh sir, then because how much you know English, I think one would learn better in the mother tongue. That's what I think. Even now, for me, now I am close to die, but still if I am learning something, I think I am more compatible with Sinhala, I guess. That's what I think. But of course, when I was in campus, I really needed in Sinhala. Anyway, let's see whether we can prove sup E is equal to 1. Prove that before we go to chapter 1. Because the thing I am very worried is that I am lecturing here, actually not, I am not lecturing. I have that feeling. Because I don't talk to you, I go talk about the Axiom 1, 4.1.4 lemma. I have that sort of feeling because of the style. Prove that. So the only thing I guess you got from me is logical part you have more or less got it. But analysis part you haven't got so far from me. I mean what you have got is not enough for me. That is because of I'm following the text, that's the reason. Now let's see. I mean he doesn't say prove that should be equals to 1. No. Actually he says, you know, the thing is, sometimes he is so rigorous. He wants to prove that if you take a finite set of elements to prove that it is bounded. I mean, it goes without saying, no? If you have, say, some A1, A2, A3 in a set, why this is a finite set, no? This is bounded. Why? Because if you take the mod A1, mod A2, mod A3, this set, one of them is the largest, no? One of them, they can be equal. One of them is the smallest. So it is, all these are smaller than, less than or equal to this largest one. Nothing to be proved. He proves that. There is a theorem here, or lemma, or proposition. But he doesn't prove this. I think this is far more important than this one. This one, somebody can say it goes without saying. But here, let's see whether we can prove. But maybe this book is, you know, targeting for something else, that not really analysis. It does analysis, but okay. So should prove. First we have to show that it is an upper bound. So we can say it is. This means actually set of all x belongs to R such that x is strictly greater than 0 and is strictly less than 1. No? We call it the open interval, right? 0, 1. It is clear that for each x belongs to 0, 1, x is strictly less than 1. I mean, it goes without saying. So, I can say less than or equal to 1 also. So, thus 1 is an upper bound. Thus 1 is an upper bound of E. Now I have to show that it is the smallest upper bound, in the sense that if you take, according to him, in the sense that if you take any other upper bound, then you have to show that lambda greater than or equal to 1, either lambda equals 1 or lambda is strictly greater than 1. So, as a result, let's see whether we can prove it. But he has taken that for granted in the book. If you, I don't think you remember now, but go through it, you will see it. Let lambda be an upper bound of E. Now I have to show that lambda greater than or equal to 1. Can you prove it? Let lambda be an upper bound of E. But we can say for every x belongs to 0, 1, x less than or equal to lambda. That we can say. But I am asking, can we prove that lambda greater than or equal to 1?
Let's say therefore lambda is greater than or equal to 1.
What?
Because it is upper bound.
Since lambda is an upper bound, upper bound of E, you are saying?
Lambda is greater than or equal to, no, greater than or equal to 1.
Why? That's what we have to prove. I mean, of course, it is, but we have to prove it. We can say lambda greater than or equal to any real number x less than 1. That's the meaning of lambda is an upper bound of E. What I am pointing to you is that we have to prove it. Since lambda is an upper bound of E, we can go for the Kokata tile in the sense that's proved by contradiction. Let's see whether that works. Left lambda be an upper bound of, we need to show that my worry is that you haven't got to the proving. You haven't got the proving character yet. Logical character you have got reasonable to a reasonable level, but not the proving. We need to show that lambda greater than or equal to 1. If you want, we can assume to the contrary. Assume that lambda is strictly less than 1. So now I need a contradiction somehow. To the contrary, assume that lambda is strictly less than 1. Now, this is the real line. Here is 0, here is 1. We are assuming to the contrary, assume that lambda less than 1. Lambda is somewhere. Lambda can be here, lambda can be here. Anyway, if lambda is greater than, so you can say clearly lambda is lambda greater than 0 or lambda less than or equal to 0. If lambda, suppose lambda greater than 0, then can you get a contradiction?
Can't we say that since lambda and 1 is a real number, there exists x belongs to E such that lambda exists in between lambda and 1?
In this case,
yeah.
suppose lambda greater than 0. However, without saying what you are saying, thus what you have said is correct. 0 less than lambda less than Because in this case, to the contrary, assume that lambda less than 1. Now lambda belongs to E. So lambda belongs to E. Now, do I have a contradiction now? Lambda is an element of E. Is there a contradiction? Yes or no? What is the contradiction?
Because we need to show that lambda is greater than or equal to 1. All the element in E is less than 1. Therefore, lambda is a contradiction.
What is the contradiction? I didn't get it.
It says that we need to show that lambda is greater than or equal to 1.
Yes.
Now we have shown that lambda is an element of E.
Yeah.
All the elements of E is
Less than 1.
Therefore,
So that is a contradiction. You follow it? Contradiction. I will write contradiction. Very good. Now suppose lambda less than or equal to 0. Now can you get it? See, what I am after is that because I am not spending time with you according to me proving analysis things. I am talking about lemma for one for propositions for one e. This and that, not in an analysis manner, my behavior is different here. So these are the analysis ways. You need whatever you know, you have to do it. You are doing analysis means proving always. Now suppose lambda is equal to 0. We need a contradiction. That means lambda is here now. Can you give me a contradiction?
Here is 0.5 is an element of E and 0.5 is greater than 1.
Clearly, 1/2 belongs to E and 1/2 greater than lambda. So this is a contradiction to lambda is an upper bound. This contradicts. The fact that lambda is an upper bound. Right? So, if we got lambda greater than 0, we got a contradiction. Lambda less than or equal to 0, we got a contradiction. Both are contradictions. So, to the contrary, assume that lambda greater than 1, less than 1. Thus, our assumption is false. Hence, lambda greater than or equal to 1. We need to show that lambda, I have now proved it, thus. Sup 0, 1 is equal to. So this is the proof. We need to be doing this sort of things almost always. We are not doing that. So I am a little bit worried about it. Is this clear now? Because this is a real easy thing. But in mathematics, nothing can be taken for granted without the proof. No? So, similarly, you need to be able to prove that inf of E is equal to 0. We should be spending time on this sort of little things in order to be an analyst. And what I am saying is we are not doing that. So this is chapter what? Again another big thing we proved was, by the way, theorem 5.5.9, in some place one line you got stuck. I am not going to that theorem today. But can you see, this is on page 118. Can you remember he said that k by n is an upper bound of A and L by n is not, we can find an integer n between L and k with the property that etc. I want you to, before when you, today is Friday or Wednesday? Today is Wednesday. So before you come on, not before you come, I want you to go through the, except that line, the other things of the proof carefully, because they are very easy, other parts. So I will talk about this line. So because this, we are going to use always know that if a set is non-empty and has an upper bound, it has a less upper bound. This is the proof. So that day we sort of got stuck in that line. Since k by n is an upper bound for E and L by n is not, we can find an integer mn between L and less than or equal to k with the property that. If you can understand that line also, good. But I want to make sure, assuming that line, see whether you can understand the rest. According to me, they are very easy. But I shouldn't say anything easy because, I am too old, I have done this thing for many years. When I say it is very easy, it doesn't make any sense. It is something you should say, easy or not. So that's not I should not do that. Again here, another thing is, we have done something very important. We don't have time to emphasize. No? If you have a number x greater than 0, you have a real number x and n is bigger than or equal to 1. Actually, let's say greater than 1 especially. Then we want to define x to the 1 over n. What there is one advantage, however. Now, if you are given an integer n, you can define x to the n very easily. I am talking to a man in the street, x to the n, you can say you multiply x by itself n times. So that is x to the n. So it makes sense. No? And if you ask x to the 1 over n, you can say x to the 1 over n is a number y. When you multiply y by itself n times, you get x. So x to the 1 over n also has a meaning to a man in the street. X to the n is you multiply x by itself n times. X to the 1 over n is a number y. When you multiply y by itself n times, you get x. But if somebody asks you x to the root 2, if you ask me the meaning of 3 to the root 2, you cannot say anything. The first thing is you don't know what the hell is 3. Forget about root 2 even. No, let's leave it. Since you have a computer or calculator, you can compute 3 to the root 2. And you don't know whether that is correct or wrong also. You just do it. Because you are told to do so. X to the n has a meaning for us, to a man in the street. X to the 1 over n also has a meaning to a man in the street, but man in the street cannot find x to the 1 over n. How can you find y such that when you multiply y by itself n times you get x? No way, no method. Of course, we have calculator, computer, this and that. We get it. But 3 to the root 2. You find this number y, you multiply y root 2 times. Doesn't make any sense. So 3 to the root 2 is a meaningless thing. Meaningless thing. For anybody. 3 to the root 2. What does it mean? If somebody asks me, actually, I cannot reply. I can reply to some maths people, but again, that's not a fair answer. 3 to the root. Before going to that, however, I guess in chapter, we haven't discussed this, no? This comes in chapter 6, I guess. I cannot remember. Exponentiation. So I'm also out of real exponentiation part.
Yes, in 5.6 page 121.
121.
21.
You have real exponentiation part. No, he has only, it's the 1 over n. It must be in chapter 6. It must be. I don't remember because I also read all the chapters always. Okay, so now we really have a meaning for this. We have a meaning for this, but we cannot compute. We don't have a meaning for this at all. 3 to the root, what on the earth? And doesn't make any sense. Anyway, so since we are done with this, by the way, at the very beginning, we are not going to, we haven't seen anything about this. Now, we did define x to the 1 over n. X to the 1 over n, what is the definition? X is a positive number, x to the 1 over n is the supremum of set of all y belongs to R such that y greater than or equal to 0 and y to the n less than or equal to x. This is the definition. So sup comes there. So sup is a very extremely important word. Sup and inf. You need to learn. Sup, inf, Cauchy sequence. Among the words that you have learned, they are the most important words as far as analysis is concerned. So this is the definition. This one is the one you pointed out that on page 122 he has given this definition. Then you may run into a different question, however, if let's not go for the time being. Now, we have been through the proofs. I mean, I should not say I just read in front of you and you understood them. Here he is saying on page 123, without going to chapter 6, I am doing this thing because it is very important. He has a proof, lemma 5.6.5 on page 123. He is proving that let x greater than or equal to 0 be a non-negative real and let n greater than or equal to be a positive integer. Then the set E, that set of all y belongs to R such that y greater than or equal to 0 and y less than or equal to is non-empty and is also bounded above. That's what he is proving on 5.6.5. You can understand that proof, no problem, if you read it carefully. In particular, x to the 1 over n is a real number because he is proving that this set is non-empty and bounded above. Then that theorem that I told you before I go through it, see whether you understand, except that line, this set is non-empty and bounded above. By that theorem, then it has a sup. That sup is x to the 1 over n. So it kind of makes sense, no? Y less than or y to the n less than or equal to x. For us, this is y less than or equal to x to the 1 over n. No? So this definition makes sense. Makes sense. So now you need to remember this is your definition of x to the 1 over n. Very important. Very, very important. If somebody asks you what is the definition of x to the 1 over n for x positive number and n is a positive integer greater than 1, if n is equal to 1, I mean there is nothing here. So this is the definition. So I mean if you look at lemma 5.6.6, let xy greater than or equal to 0, this is on page 123. There is a very good first problem. It says let xy greater than or equal to 0 be non-negative reals and let nm greater than or equal to 1 be positive integers. First one is if y is equal to x to the 1 over n, then y to the n is equal to x. Can you see? Then y to the n. So in a sense x to the 1 over n, if you multiply n times, you get x, no? Can you do it that way in this? You cannot do it like that, no? You have to prove that, because that is how he defines x to the, now that is how he defined square root 2, no? We have proved that there is no rational number x such that x squared is equal to 2. But he proved, he considered the set of all y belongs to R such that y greater than or equal to 0 and y squared equal to 2. Y squared less than or equal to 2. I said it wrong. So, supremum of that set was called root 2 actually. Then he has proved that over there in that proof. He has proved, he did not say root 2 times root 2 is 2, no. He proved separately that that sup squared is equal to 2. Here again, actually we have to prove that this sup raised to the power n must be equal to x. Again, then I looked at his C exercise 5.6.1. Then I read the question, exercise 5.6.1, hints, review the proof of proposition 5.5.12. That is where he proved square root of x squared is equal to x. I'm sorry, square root of 2 squared is equal to 2. That is the place where he proved it. Also, you will find proof by contradiction a useful tool, especially when combined with the trichotomy of order in proposition 5.4.7 and proposition 5.4.12. The earlier parts of the lemma can be used to prove later parts of the lemma with part C. First show that if x greater than 1, then x to the 1 over n greater than 1, etc. I did some parts of this problem, I did not do all of them. I was going to try the last problem, mod x equals x squared to the 1 there, then I forgot. Can you see he on, where is this thing, very, on page, he has proved proposition 5.5.12. He has proved that there exists a real number x such that x squared is equal to 2. Then he considered the set of all y belongs to R, such that y greater than or equal to 0 and y squared less than or equal to, y squared strictly less than 2. Doesn't matter, it is less than or equal to 2, even if you write like that. Anyway, he has proved that that is non-empty and bounded above, therefore it has a sup. Then he has proved that that sup, he has taken that sup as x then he has proved x squared equal to 2. So it is a proof. Here he says, look at that proof, but x squared and x to the n are different. So let's prove this one to make sure that at least we know how to do this. And then let's go to chapter 6, because I thought the way it is going, not that comfortable with it. Again, some people go on trips, they come empty-handed even without some couple of apples, say. People have gone, no, I don't know. It's not the way to go on trips, no? If we were on the trip, we would have bought many things for the rest of the people in the class, no?
Yeah. Still a child, no sir.
Buddha, you said still?
A child, no.
Still a child. He is a child. Plus, you are 18 or less than 18? 8.
18.
18. Maybe you are the only 18-year-old kid that I talk to about this rigorous mathematics. Okay, let's show that what if y is x to the 1 over x. Let me write. Oh, I wrote on a piece of paper. These are not. By the way, there is this worksheet. I have.
use
You said. Okay, I have said that 4.1.8 make a mark and 5.1.1. I need solutions separately. You write on a piece of paper. I want to see how you write, because you know this person is grading. And 4.1.8. 4.1.8 and 5.1.1. You write the solutions for these two problems on a piece of paper and hand it over to me. 4.1.8 and 5.1.1. I was thinking I should also go through your solutions for one or two problems. You are giving them to him, but I am asking in addition to that. Submit before we do. Okay, let's prove this before we go to chapter 6. According to this book, this is lemma 5.66. I have written that also. 6. Let x greater than or equal to 0 and n greater than or equal to 1. You should go through this carefully of the proof of 5.5.12, very important, because he has proved there square root of 2 squared is 2. That's a good proof, very good proof. Let x greater than or equal to 0 and n greater than or equal to 1. 8. And I thought of if y is equal to x to the 1 over n, then y to the n is equal to x. Because the thing is here, we cannot, somebody grades 80 student will say it goes without saying, because he multiply y and time to get x, but here to us y is the supremum of that set. Proof. Suppose y is equal to x to the 1 over n. Okay? What is what x to the 1 over n is? The supremum of set of all, say t belongs to R, such that t greater than or equal to 0 and t to the n less than or equal to x. Right? This is the definition. So let me say let E is equal to this set. Set of all t belongs to R such that t greater than or equal to 0 and have you done this? Not yet, no? Less than or equal to x. Let's take this set. Actually he has proved on page 123, this set is non-empty and bounded above, but let me do it again to make sure. First, let us show that he is non-empty. We want to show that he is non-empty. Let T 0 is equal to, you are given x is given to you, x over 1 plus x. Then definitely x is greater than or equal to 0, then 0 less than or equal to c0 certainly strictly less than 1. Right? If t0 less than 1, t0 to the n power also less than 1 by induction. Thus by induction on n I have to behave like a lecturer today. Thus by induction only. On n, t0 to the n less than or equal to t0 is simply less than x. T0 is strictly less than x, no? X over 1 plus x is less than x. I mean, this one you can prove by induction, no? Since T0 less than 1, you say P, let P and be the statement T0 to n less than or equal to T0. P1 is of course trivially true. Assume n is an integer such that Pn is true. Can do it, no? Thus, T0 belongs to E. Right? Therefore, E is non-empty. So, E is non-empty. Of course, he has proved this thing in a different way. Second, first let us show that, then second. Let us show that E is bounded above. By the way, I forgot to tell you that we can take the break at 11 o'clock every day, even including today. So let us show that E is bounded above. By 1 plus x. I want to do that. So let T belongs to E. Then T less than or equal to 1 for T greater than 1. 1 of them. Suppose T less than or equal to 1. then definitely t could have 1 plus x. T less than or equal to 1. No, it's trivial. Now suppose t greater than 1. Suppose t is strictly greater than 1. Then t certainly less than or equal to t to the n. Since t greater than 1, t to the n gets bigger. T to the n, since t is a number belongs to A, t to the n less than or equal to x. Definitely less than 1 plus x. That is I began t here, ended up 1 plus x here, that is t less than 1 plus x. If t less than or equal to 1, t less than 1 plus x. If t greater than 1, again t less than 1 plus x. Thus, is bounded above by 1 plus x. Right? Now t is a subset of R, not t. Clear? E is a subset of R. E is a subset of R. E is non-empty, which is bounded above. Then by that axiom, not the axiom, so I use that theorem, E has a least upper bound, should it exist. Hence E has exactly one least upper bound, E has exactly. One least upper bound. What? Right? Again, I ask you to go through the proof, except that line, that I will talk about that line next day. So now this set, this thing exists for sure. That's what I have done so far. So y equals sup E. By definition, it is x to the 1 over n. So there is a number called y. By definition, it is x to the 1 over n. One thing I know is that clearly y greater than or equal, this t0 is a number in the set. No? T0 belongs to it. Therefore, y greater than or equal to T0. Right? Y greater than or equal to T0. T0 is definitely greater than 0. We show that this is the thing we want. Now we are coming to the problem actually. We show that y to the n is equal to x. Actually, the thing is, we write like this. Actually, this is just a symbol. So far, we don't know it is x to the 1 over n. We just say it is. It is like when I was in USA, there was a boy. His name is Goodman. Goodman. It's not that he is good. My name is good. I have a good story about Goodman. I'll tell you some other day. Not today. Not in the lecture time. While we are talking. Okay. We show that y to the n is equal to x. Clearly, y to the n is strictly less than x. O y to the n greater than x. O y to the n is equal to x. Try to no real numbers. Two real numbers. One of them is true. So I have to prove that these two are not.
Can you say have to take or
Okay, you do it. N less than x, so y to the n greater than x, so y to the n is equal to x. So I have to prove that first two won't hold. Then what remains is the last one. First assume that y to the n is strictly less than x. Choose epsilon greater than 0. So that 0 less than, of course, epsilon less than 1 and epsilon is strictly less than x minus y to the n divided by 3y raised to the power n. I forgot something. I have to do something here. Easy thing first. Result. I will go into result. Let n belongs to Z plus. And 0 less than epsilon less than 1. Because I need this result here, that's why. Then 1 plus epsilon raised to the power n is strictly less than 1 plus 3 to the n times epsilon. This result will be used in this proof. So, certainly this will be proved by using induction. Let P and be the statement. One plus epsilon raised to the power n is strictly less than 1 plus 3 to the n times epsilon. Since 1 plus epsilon is strictly less than 1 plus 3 epsilon, when you put n equals 1, you get 1 plus omega 3. P1 is true. Right? Let n belongs to Z plus be such that En is true. Right? That is 1 plus epsilon raised to the power n is strictly less than 1 plus 3 to the n times epsilon. Right? Notice that 1 plus epsilon to the n plus 1 is 1 plus epsilon raised to the power n times 1 plus epsilon. However, this guy less than 1 plus 3n epsilon times 1 plus epsilon. Right? This one equals 1 times 1 is 1 plus, and you see for all the other terms epsilon is a common factor. Epsilon is common, so I pull out epsilon, right? What else is there? Here when you multiply 3n epsilon times epsilon, you get 3n epsilon square. So I took 1 epsilon out and I write 3n epsilon here. Oh. Then you have 3n epsilon times 1, then I get 3n only. Then you get 1 times epsilon, so I have 1. Right? Then this is strictly less than 1 plus 3 to the n epsilon, definitely less than 3 to the n, because epsilon less than 1. This guy remains the same. 1 is also less than 3 to the n times epsilon. So this is equal to 1 plus 3 times 3 to the n is 3 to the n plus 1 epsilon. Thus Pn plus 1 is true. So it is a very simple thing. Hence by induction, we have shown that P1 is true. We have taken an integer n such that Pn is true. We have proved then Pn plus 1 is true. Therefore, by induction, for each n belongs to Z plus. Pn is true. That is induction. Thus, for each n belongs to Z plus 1 plus epsilon raised to the power n is less than 1 plus 3 to the power n. So I proved that it is a very simple thing. It's not difficult at all. But I will use it here. First, I guess I wrote first. Now back to the proof. So far, I haven't done anything. Actually, what I have done is done on the page 123. I wrote different statements than from the book. So I have proved that that's it. Is non-empty and bounded above is the subset of R. Therefore, by that theorem, I ask you to go through. Next day we are going to discuss about that line and the importance of that thing. So it has a sup, I call it Y. We need to show that yn equals x. So we use the trichotomy for these two real numbers. Yn less than x, Yn greater than x, Yn equals x. So first I assume that Yn less than x. I choose epsilon greater than 0, so that epsilon less than 1 and less than this number also, because this is a positive number. Then from our result, I can say y to the n times 1 plus epsilon raised to the power n. This one is strictly less than y to the n times 1 plus 3n epsilon. So that is, it comes right away. This is equals y to the n plus 3y raised to the power n times epsilon. Three y to the n times epsilon less than x minus y to the n. Epsilon times 3y to the n. So I can write this is less than y to the n plus x minus y to the n. This is equal to x. Right? So now what I have proved, thus y times 1 plus epsilon raised to the power n is less than x. This is a y is greater than or equal to 0, y is positive actually. 1 plus epsilon is of course positive. So less than x. My set E is t to the n less than x, less than or equal to x. Therefore, y times 1 plus epsilon belongs to E. But this is bigger than E. Sorry, bigger than y. Y is the supreme. So this contradicts. Since y is equal to E, we have reached a contradiction. So yn less than x cannot hold. Right? Second assume yn greater than x. Now choose epsilon greater than 0. So that 0 less than, of course, less than 1 and epsilon is strictly less than y to the n minus x, which is positive, divided by 3n raised to the power x. So let's go through the x greater than 0 case. Let's take that one because x equals 0 case is trivial. Otherwise I cannot write things. Then x times, and you read, if you multiply 3nx here, you get epsilon 3nx. Then if you bring x to this side, plus x, then x is common for both terms. So then you get then x times 1 plus 3n epsilon less than yn. Right? again by our result. Our result x strictly less than, so this is positive, y to the n divided by 1 plus 3n epsilon. So x less than y to the n divided by this guy. However, 1 plus 3n epsilon, it is less than 1 plus epsilon raised to the power n. We proved 1 plus epsilon to the n is less than that. So this is exactly y over 1 plus epsilon whole thing raised to the power n. This is than that. Machines. Y over 1 plus epsilon is strictly less than y. Y is the supremum. Y over 1 plus epsilon. There is t belongs to it. Such that y over 1 plus epsilon, there is a t in between because y is the supremum, so there must some t belongs to E, and hence y over 1 plus epsilon raised to the power n is strictly less than t to the n. T to the n we know definitely less than or equal to x. T is in the set. Here you have, I guess, x is strictly less than y over 1 plus epsilon raised to the power n. Here you say y over 1 plus epsilon to the n is strictly less than x. So 1 and 2 contradict. If you want, you can write then x less than again without writing this way. X less than y over from 1. So contradiction. Contradiction. So y in less than x cannot hold, y in greater than x cannot hold, thus y n doesn't have any choice rather than getting married to x. Y n is equal to x. So it is more complicated than square root of 2 square is equal to 2. More complicated because of nth power. Clear, no? Proof is clear. So again there is here, this is part A. If y is equal to x to the 1 over n, then y to n equals x. So this is a complete proof. Conversely, if yn is equal to x, then y is equal to x to the 1 over n, then that you can do it. Third one, see x to the 1 over n is a positive real number, of course that's easy. D, we have x greater than y if and only if x to the 1 over n greater than y to the 1 over n. That's also easy. Part E, I didn't try to do. I thought it is easy, I don't know, that's what I thought. Like that. So What main reason to do this is to make sure that y, if you are given a positive number x and a positive integer n greater than 1, x to the 1 over n is, this is the definition. This is the definition. Because say you don't have a calculator or something, somebody asks you, I mean, third root of 5. So how do you say? I mean, how do you find it? No way, no. Here this is the way to find it. Because you say y is equal to 5 raised to the power 1 over 3, then you take log L in y equals 1/3 L in 5. Like that you can get the answer using the technology, assuming technology is correct. But if somebody asks you, what is it? Then this is it. So proving x to the 1 over n raised to the power n is equal to x is not that easy. It's a complicated proof. Even proving root x squared is equal to x is also proof in the book is not trivial. It's choosing. Both these proofs are telling you that this analysis is a ball game with epsilon. This is a ball game with epsilon. When you come to soup, inf, all of them are ball games with epsilon. We discussed lim soup, not yet, no? No, luckily. Again, the lim soup definition in this book, I am not that, it is correct, but Sudha, you have all of them. Not that, though correct, you know, certain things must be put in the right way. So what else I was going to tell you forward? I talk about soup, no soup. Now, let's go to now chapter 6. Limits of sequences.
So it's better if we take a break now. It's 10:50.
Okay.